Okay, this video is to assist you with graphing the polynomial functions. To further assist you, I'm going to instruct you to go to page 326 of the textbook, and you will find an outline in the box with 5 steps recommended for things that we should look for. So we'll get going here on this. This is a polynomial function of degree 3, and therefore we expect to see 3 zeros for the function. That means 3 x-intercepts. That could be some with a higher multiplicity than 1, but we'll see here. Now, the first thing we want to do, I'm going to follow through the steps here in the book. We want to use the lead coefficient to determine the graph's end behavior. So the end behavior for this particular one is that since it's an odd power, x to the 3rd power, and that's a positive x to the 3rd power, there's not a negative sign in front of that, we know that this function is going to decrease to the left and it's going to increase to the right in the end. In between, it could do different stuff, but we know the far left and the far right behavior of that function will be as such. Second one, we're going to find the x-intercepts, and we're going to set this whole function equal to 0, and we're going to go ahead and find the x-intercepts. So when I go down here to get my x-intercepts, I take x cubed plus 2x squared minus x minus 2, and I'm going to set it equal to 0. So we're going to go ahead and factor this guy. This one works out as a grouping, just like a couple of the ones we did in the previous video. So out of that first term, hopefully you're getting the hang of this by now. You can pause the video and try this if you want, and then resume. Take out an x squared, leaving an x plus 2. In the second one, so that I also get an x plus 2 in the parentheses, I'm going to take out a negative 1. And since both terms have x plus 2, I'm going to factor x plus 2 out of both of those terms, leaving me x squared minus 1. And going a little further here, x plus 2 times x plus 1 times x minus 1 is how the difference of the two perfect squares factors. So if those 3 things are multiplying to equal 0, then we know that either the x plus 2 must equal 0, or the x plus 1 must equal 0, or the x minus 1 must equal 0, giving us 3 zeros. One is at negative 2, one is at negative 1, and the one on the right is at positive 1. So those are the 3 places where the x-intercepts will be intersected. These are multiplicity 1. It's not coming from x minus 1 squared or x plus 1 squared or x plus 2 squared. These are multiplicity 1. So we are going to expect the graph to actually pass through the x-intercept at those places. So going on, the next thing they're going to ask us to do is to find the y-intercepts. And that's pretty nice, because to find the y-intercept, I just substitute in x equals 0. Well, if I look at the original function up here, putting an x value of 0 in is going to cancel out everything that has an x, leaving us with a negative 2. So that's a quick one. We know that the y-intercept is going to be negative 2. Now, symmetry. We haven't talked about it since chapter 1, but sometimes having a little knowledge about symmetry will help us out. Other times it won't. So what I'm going to do is I'm going to figure out, based on the original function, our original function up on top here was x cubed plus 2x squared minus x minus 2. I'll write that here. And I want to compare that to f of negative x. Basically, I want to figure out, is this an odd function, is it an even function, or is it neither? If it's even, I know I'm going to have symmetry across the y-axis. If it's odd, I know I'm going to have symmetry across the origin. And if it's neither, then I'm not going to be looking for any particular symmetry. So we're going to go ahead and substitute in with parentheses, and the exponent staying outside of that parentheses. So I'm just putting negative x in everywhere that x occurred. And then we're going to simplify that. So if I take the negative x to the third power, that becomes negative x cubed. However, the next term is going to be positive because negative x squared is positive, and so it becomes just plus 2x squared. The next one's plus x, and the next one stays as a minus 2. So I want to compare these guys. If they're identically the same, perfectly the same, that's called an even function, and we're going to have symmetry across the y-axis. If they're exact opposites, that would mean that I would have a negative x cubed, a negative 2x squared, a positive x, and a positive 2. I don't have that either. So these are neither. So we do not have any particular symmetry here that we are going to see. However, one little last piece of information that we need to know is that when we have, or whatever our degree is, this is a degree 3, that means that we are going to see one less than that. So 3 minus 1 is 2. We are going to see 2 turns in the graph. So we may see something, we know that based on the end behavior, we're probably going to see something along the lines of this. Because we know it falls to the left, it rises to the right. We're going to have our x-intercepts and our y-intercepts in there, but we know it's going to take 2 turns. And the 2 turns I'm talking about are, that's a turn, and that's a turn. And that's what this little thing tells us. So always, no matter what the function is, the degree of it, if it said x to the 7th there, for instance, then I know it's going to turn 6 times when we graph it. So I'm going to take this information that we found out, and we're going to put it on a graph and see what we end up with here. So my x-intercepts were negative 2, negative 1, and 1. So I'm going to go here, and at negative 2, negative 1, and 1, I'm going to put those intercepts. Also, looking back on the other sheet, we figured out that the y-intercept was at negative 2. So I'm going to plot that. And based on the other guy, we knew that there was no symmetry, and the graph is going to take 2 turns. So at this point, we would go here and say, well, the best we can do is say that it's going to do something, and it's not a perfect graph, but if we wanted that, we'd have to plot some more points. But it's going to do something along the lines of this smooth and continuous graph. And you can double check that by putting the original function, which is this guy. You can put that into your calculator, press graph, and make a comparison. So what I think we ought to do is probably give you guys another graph here to try. There's enough time left in the video to do so. So we'll go ahead and we will try the graph. We're going to do h of x is going to be equal to x to the 4th power minus 2x squared plus 1. So going along the same set of steps, we are first going to determine end behavior. Now this one here, the degree is 4. That's even, so we know this is going to behave much like the y equals x squared graph. And we have a positive coefficient in front of there, a positive 1. So I know that this is going to rise to the left, and it's going to rise to the right. Second step, after we find that, we're going to find our x-intercepts. We are going to find our x-intercepts by taking the function and setting it equal to 0. Now this guy here does factor. It might not jump right out at you because you're used to seeing x squared as the lead coefficient, but this factors as x squared minus 1 and x squared minus 1. If you double check that, you would multiply that and get x to the 4th minus 2x squared plus 1. So both of these are an x minus 1 times an x plus 1. And this second one is an x minus 1 times an x plus 1. Which you may sometimes see written as x minus 1 squared and x plus 1 squared. Bottom line is that we have 2 of those, and I have 2 of those. So we are talking about multiplicity 2 for both of these guys. So what are the x values that would make this equal 0? Well, x minus 1 equals 0 when x equals 1. X plus 1 equals 0 when x equals negative 1. So I'm expecting to see the graph touch but not go through the x-axis at those 2 locations. So we'll go down here and we'll find our y-intercepts. The y-intercept, remember, all we do to do that is to find that is we plug in the x value of 0. We'll look at the original equation here, the original function. If I put in an x value of 0, I'm going to be left with 1. So that's my y-intercept. After finding that, we're going to look for any kind of symmetry. So once again, let me rewrite the function down here so we can compare it. X to the 4th minus 2x squared plus 1. That was my function. I believe I called it h of x, was it? Let's see here. Yep, I called it h of x. So we are going to find h of negative x to check for any kind of symmetry. So I'm going to put in parentheses negative x to the 4th power minus 2 times negative x squared. Oops, I forgot the plus 1 out there, didn't I? Yes, I did. And let's see how this thing compares. Negative x to the 4th is going to be the same as positive x to the 4th. The negative, or minus 2 times negative x squared is going to stay negative 2x squared, and then plus 1. So we are now going to compare these 2 guys. How do they compare? They are the same, which means we have an even function, which means it's going to be symmetric to the y-axis. So let's put this together and let's see what our graph looks like. Before we do that, I want to go back up here and make a correction on how I wrote this. When we wrote the x-intercepts, we said that x equals 1 is an intercept of 0, but we have to specify that as a multiplicity of 2. And the same thing with x equals negative 1. We should write that out. Multiplicity of 2. Okay, so let's go ahead and start trying to throw some of this stuff on this graph here. So starting with our x-intercepts, we knew 1 and negative 1. There's one there. There's one there. Looking back, we have a y-intercept at 1. And we know that the right and left behavior is going up. And we know, because of the test for symmetry, we know that this graph is symmetric to the y-axis. So this graph is going to do something along the lines of this. A smooth curve. Again, plug it into your calculator, check it out, and compare the two, and use that as a good learning tool for you. I hope this helps. I have to end this video now.